All right, guys, I would like to pick up where we left off on Friday. Might even just spend the entire period talking about exactly the same thing we talked about on Friday. For the mere fact that if you do not understand what we're doing and why we're doing it, it's going to make the rest of the class a nightmare for you. Okay? But if you get a good understanding of this why, it'll make the procedures down the road make more sense and allow you to kind of augment those procedures if you need to. It'll help you realize relationships a little bit easier as we move beyond this, okay? Trigonometry, I think, is a course much like geometry where if you can establish relationships, it makes things so much easier, okay? But you need to understand this in order to establish those relationships. Yeah. So, in the first quadrant here, I've got an angle. Okay, this black ray down here is my initial ray. The blue one is my terminating ray. Okay, on that blue ray is a point. Okay, and there's actually an infinite number of points, and I don't care which point we choose right now. Okay, but just to kind of prove a point to you, if I use that point C and construct a right triangle off of that point C with this ray down here, and I do the same exact thing with G, what I end up creating here is obviously two triangles. But let's look at getting those segments created. So that segment and that one. All right, so I've got segment DC and segment HG. Is that okay with everybody? Okay. Now, when I look at segment CD, it's attached to right now that red triangle, correct? If I were to take the length of, let's just say, CD and divide it by the length of, let's say, AC. Okay, so I'm taking this segment here, which would be opposite segment to that angle right there, correct? And I divide it by the hypotenuse. Okay, so that is the AC. Hit enter, usually gives me 0.88, right? Okay, that's great, that's fine. Now, what I'm going to do is focus my attention on that triangle. So now the opposite side would be GH, and now the hypotenuse would be AG. If I divide them, still 0.88, right? Do I really care where that point is? Is that, as I move that, those distances of GH and AG, respectively, are changing here, right? But is the quotient of 0.88 ever changing? No. Okay. So it doesn't matter ultimately when we're done with this whether I use point G, point C, or any of these other points throughout here, or any of these other points that would be extended on this ray. Okay. Now what I'm going to do is ask my calculator, instead of even looking at those distances, can my calculator tell me what the opposite, so sine, opposite divided by hypotenuse, so that's the sine command, of that angle of 61.35 would give me, so of alpha, same 0.88, right? Okay, so that's how that sine of alpha is defined as the opposite of the right triangle, the opposite side of the right triangle in reference to the angle, divided by the hypotenuse. Okay, so that idea should hopefully make sense to us, and that's ultimately why, as we go through some of this discussion, a lot of times I'll go back and forth about talking about this point and using this point, and sometimes I won't, because it doesn't matter what that point is. Does that make sense? Okay. So let's do this then. Let's talk about having an interest in, So generally speaking, what we do is when we have this terminating ray, no matter where it's at in our coordinate plane, we like to turn it into a right triangle. So usually you just see this, okay? And let's say that my angle is over here. Let's say my angle is 130.07 degrees, okay? And I want to know the sine or the cosine or the tangent, secant, cosecant, cotangent about 130.07 degree angle, okay? Well, the way that you address that is you really don't deal with the 130.07 degree angle, okay? You're going to always take from your terminating ray a point on it. I usually use the end point of my ray or the tip of my ray the way I've drawn it. And I'm going to draw it straight. I'm going to draw an altitude of a right triangle straight down to the x-axis. So that's going to give me that segment right there. Does that make sense? I'm always going to have either the positive or negative x-axis. So I'm going to draw that part of the negative x-axis. And basically what I do is I just created two legs of a right triangle, correct? Okay. And now my hope is that you can see this right triangle. Okay, is everybody okay with that? Now, this angle right here, where my cursor is the angle that I'm really going to deal with here. Okay, how can I find that angle? 180 minus 130.07. Okay, what that angle, and hopefully the demonstration today is going to confirm this for you. That angle is going to tell me every single thing I need to know about 130.07. And just so that I can make things a little bit easier in explaining, let's do that. Let's look at a 129.81 instead. Okay, but if we can justify this with that information, we should be able to do it for any location in the coordinate plane. Okay, so what I'm going to do is I'm going to ask GeoGebra to take 180 degrees and subtract from it this angle alpha and see what it gives me, 50.19. So what I know about 50.19 should tell me everything I need to know about 129.81. Okay? Except for the plus or minus aspect. Okay? The SIGN out in front. And we'll talk about that here in a moment. What I'm going to do right now is I'm going to take this information that we just created, and I'm going to take this angle of beta, and I'm just going to allow GeoGebra to use a protractor and basically just replicate that beta for me over here. Okay. So now, using the logic that we talked about before, no matter what point I choose over here, okay, I will always end up with a right triangle, correct? What can you tell me, or what do you think you know about this triangle over here in comparison to this one here? They're proportional. They're similar, okay? And a unique characteristic about similarity, a unique kind of instance of similarity is actually congruence. Okay, and I put that on the wrong graphic, so let's go 10, 12. So if I go to there, this, I don't know, I'm zoomed out, different scale, but this triangle here is now congruent to that one. Does that make sense? So if I were to take, let's say, this distance, I to j or L to j down here, and compare it to L to E, okay? So let's go LJ to LE. Compare those through division. Do I get the same 0.77 that I was getting over here with this information? Does that make sense to everybody? So my hope is that we see that angle in the first quadrant tells me everything I need to know in regards to the sine of the angle that's existing in the second quadrant of 129 degrees. Is that okay with everybody? All right. Now, that can be a little bit misleading because what happens when I ask it for cosine? So let's go cosine of alpha. And you see there it gives me negative 0.64, right? Okay. Well, when I come over here and look at this 50.19 number, okay, so let's go cosine of gamma here. What's the difference? What's the discrepancy between those two things? The sine, the SIGN, right? Okay. And the reason there's a discrepancy there is because over here, when I was asking it and commanding it to work with the 129, the cosine is actually negative 10 divided by whatever that blue, be the square root of 244, whatever that is. Let's see here. That blue distance, 15.62. So in the picture on the left with the 129 degrees, the way we're getting that negative 0.64 is it's taking the cosine, which is the x value of point C, which would be negative 10, right? And it's divided by 15.62. Well, on the first quadrant, on the right-hand side, it's taking the coordinate for L, which is 10 comma 12. So it's a positive x coordinate divided by 15.62. So positive divided by positive gives you a positive, right? Okay. Everything in the first quadrant will always be a positive divided by positive. No matter what we do over here, our result, our quotient, is always going to be a positive number. But in other quadrants, it might be positive or negative. And that's what this whole discussion is really about, is trying to justify why this triangle here tells me everything that I need to know about this larger angle, yet I still have to then, once I find that value, determine if it's positive or negative. And it's basically because I need to know, when I do sine and cosine and tangent, am I dividing positive x's by r, negative x's by r, positive y's by r, negative y's by r, or negative y's by negative x's, negative y's, positive x's, that kind of thing for tangent. Does that make sense? So, let's grab our calculators real quick. I don't care what calculator you're using, but have a calculator out. It could be TI-30, 84, Desmos, GeoGebra. I would think Desmos would probably be, or not Desmos, TI-83, 84 would probably be most appropriate. All right, what I want you to do is take your calculator, type in on it sine. Actually, first thing, go to your mode. Because we're working in degrees, just go make sure that your degree option is toggled on. I'm just going to put the screen here so you can see what I'm typing in as well. But so we've gone through and we've made sure that is highlighted. If you don't highlight that, you're not going to see the correct relationships here. And we're using that because my alpha here and my beta are both in degrees. So now I want you to type in sine of 143.13. Hit enter. Now, as we go through this, the only thing I want you to know is that we're picking numbers off of GeoGebra here that are rounded a little bit. So that 143.13, not exactly 0.13. Okay? That 0.87 down there on 36, 0.87, not exactly 0.87. We can extend that 3, 4, 5, 15 decimal places. Okay? So there may be a little bit of rounding error here as we investigate this. But if I type in sine of 143.13, now type in the sine of 36.87. So in that case, the rounding error is so small that we're precise out to 10 decimal places here, 9 decimal places. Okay. Now what I'd like you to do, because y divided by r is sine, right? Take 12, because that's your y value here, right? Divided by c to a, which would be 20. Take 12 divided by 20. .6, right? Now, rounding error is the issue here. Okay, because the top two, sine of 143.13 and sine of 36.87. That's 0.60000, 5 zeros, 4 zeros there, right? Okay, so that's pretty close to 0.6. That's pretty close to 0.6, right? If I were to just add a couple more decimals of precision, we should be able to see. So if I go sine of 143.1301, see more precision closer to 6, or 0.6, right? And then the same thing with sine of 36.8699. Same thing. Okay. So that's the only reason that you're not seeing the 0.6 is just a little bit of rounding error. Okay. But the idea here is that the sine of 143.13 can be established through using a sine of 36.87, using the sine essentially of its supplement. Does that make sense? Okay. And what you're going to find out, what would you rather do? Would you rather deal with numbers between 90 and 180, or would you rather deal with numbers between 0 and 90? 0 and 90, right? And no matter what calculation I'm doing, if I can do work with 0 to 90 rather than 90 to 180, I would choose 0 to 90. That's really what's going on here. If I don't want to deal with that number, let's deal with that one instead. Okay. And you can see then that that is validated by, essentially sine is just taking this y value and divide it by the r value, okay, or the radius, okay. Okay, so now do the same thing, but let's go cosine. So type in cosine of 143.1301. Hit enter. About negative 0.8, right? I think is what we're going to see here. Okay. Now if I go cosine of 36.8699, I get positive 0.8. Okay. Now think about this. Think about why that's happening. Yeah, because when I do cosine of 143, I'm talking about this order. I'm using that ordered pair. I'm using that x divided by 20, right? Okay. But when I go with cosine of 36.8699, I'm now talking about this triangle over here, and that x value would be positive 16, comma 12, wouldn't it? So I'm taking a positive divided by a positive in that case. And that's why on our calculator, when we type in cosine of 36.8699, we're getting a positive version. Okay? But the positive version is still good Like I still record that value right there and use that value, but I got to know that the overall problem was actually asking us to deal with the cosine of 143. I just got to know that when I use cosine of 36, that I augment this result. I put a negative out in front of it. Does that make sense? Okay. So what I want to give you here is a relationship. It's a mnemonic device that allows us to remember which trigonometric functions are positive in which quadrants. Okay. And it's only going to be looking at sine, cosine, and tangent. So okay. We'll talk then how we get the other three, secant, cosecant, cotangent from that. Okay. But it's all about division. Okay. If we remember that sine, any point in the first quadrant here, okay, is going to be a positive x value, comma, a positive y value. Do you guys agree with that? Okay. In the way that we find r, remember r was always equal to that. It's Pythagorean theorem. Okay, because I square x and I square y, no matter what I started with, x and y, whether they're positive, negative, or zero, x squared plus y squared will always be a positive number. Okay? Square root of a positive number is always a positive number. So r is always positive. Okay? So we're going to put positive r here. Okay? Well, if I do sine of theta in the first quadrant, it's a positive y divided by a positive r. Does that make sense? What result does that give you? Positive. Okay? If I do cosine of theta, so we're talking about theta now being between 0 and 90. Okay? Cosine of theta would be positive x divided by positive r, right? So positive divided by positive is positive. Okay? And then the way I only remember those two. Because I already know that tangent is sine divided by cosine. If I take a positive sine divided by a positive cosine, tangent in the first quadrant is going to be a positive divided by positive, right? Which is just positive. Everything in the first quadrant is positive. That's why we say that word all. Second quadrant. We're looking at now every ordered pair in the second quadrant is a negative x value divided by a positive y value, or comma positive y value, and then r, again, will always be positive. So then over here, when I look at sine of theta, and now theta here would be a number between 0, or not 0, 90, and 180. Okay, so the sine would be a positive y divided by a positive r. Positive y divided by a positive r. What's that going to give me? Positive, right? You see here that I'm doing the same positive y divided by positive r that I did over here in the first quadrant, right? And that's the relationship. If I'm working in the first or second quadrant, the signs are going to be the same because I'm taking a positive divided by a positive. Okay? But cosine over here is x divided by r. And x now is negative, right? So a negative x divided by a positive r is a negative quotient. So the cosine in the second quadrant is negative. So if I go tangent as sine divided by cosine, tangent in the second quadrant is going to be positive divided by negative, which is yielding a negative result. Okay. You can see here the relationship between those two things. It's the same x, it's the same r, it's just the signs, SIGN, are different. So if I want to know the cosine of 135, I can actually use the cosine of 45 to help me get that. We're going to see that here in a little bit. But then I got to keep in the back of my mind that 135 was in the second quadrant, so when I'm done, my answer better be negative for cosine because this is showing us that cosine in the second quadrant is always negative. Okay? Third quadrant. Every point in the third quadrant is negative x, comma, negative y, r being positive. So when I go sine of theta here, so these are going to be thetas that are between 180 and 270. Sine of theta here would be negative y divided by r. Cosine of theta will be negative x divided by positive r. So sine would be negative, cosine would be negative in the third quadrant. But tangent is the quotient of those two things, sine divided by cosine. So tangent would actually be positive third quadrant, right? And for the same relationship, it's going to be a positive x, negative y over here. So sine of theta, so these are thetas between 270 and 360. Sine would be a negative y divided by r. Cosine would be now a positive x divided by positive r. So sine would be negative in the third or fourth quadrant. Cosine is positive in the fourth quadrant. Okay? Tangent then would be negative. Okay? This graphic here, if you read it from first quadrant, second quadrant, third quadrant to fourth quadrant, all sine, tangent, cosine, just pretty much every textbook is going to show this mnemonic phrase. They call it all students take calculus. If you remember that, or come up with your own phrase that has 4 words starting with A, S, T, C in a particular order, and you can remember which trig ratios are positive in which quadrants. Okay? Or just understand what we just went through. Okay? It's been several, so the last time I taught calculus, this has been probably 8 or 9 years ago. I had a kid, he would say, he went backwards and he said, all calculus teachers suck. Okay, so he was able to remember it that way. But he had me, so I totally proved that wrong. But somehow divides away. So now then that's only for sine, cosine, and tangent. There's 3 other ratios, right? Secant, cosecant, cotangent. But they're reciprocals, right? Is the reciprocal of a number the same sign, SIGN? If I have negative 1/2, what's its reciprocal? Negative 2 over 1, right? So the sine, wherever the sine is positive, its reciprocal, cosecant, would also be positive. Okay, wherever tangent is positive, its reciprocal, cotangent, would also be positive. Same thing for cosine and secant. Okay? So that little phrase should help us decipher where all 6 trig ratios are positive and negative. Okay? So let's do some examples here. Okay? Now, these examples here that we're going to work with, we can do it 2 routes. Okay? We can actually work with exact values, or we use our calculator to find estimated rounded values. Okay, we'll do it both ways. But generally speaking, as we move on after today, when you have the ability, they won't tell you, but when you have the ability to find exact values, they want exact values. Okay? And we'll see here why that may be the case in this question. So we're looking and trying to evaluate cosine of 135. So the first thing you're always going to do with these, it doesn't have to be a great sketch. It doesn't have to be to scale, but it does have to, points have to end in the right quadrant and all that kind of stuff. Or angles have to end in the right quadrant. This thing's being a little, turn it off. So what we're going to do is we're going to draw an angle theta of 135. So we know that that's 90, obviously. That's 180. So 135's got to be somewhere in there, right? Between 90 and 180. Okay, so this green angle here is theta. Okay? And if I'm interested in that theta, I'm never going to deal, especially when, as long as theta is bigger than 90 degrees, I'm never going to directly deal with it. Okay? So right now, that's theta. I'm going to take from my terminating ray. The reason we can do this is that if I draw that ray down, or that, we'll call that an altitude of that right triangle right there will be similar to me taking this point here, drawing straight down, and drawing that right triangle. Does that make sense? Okay, which would be then similar to any one of the right triangles that any one of you draw on your paper. Okay, because they're all going to have that 90-degree angle, and they're all going to have that supplement of 135. Okay, what is this angle right here going to be? 45 degrees. Okay, that's the angle that I'm going to deal with. Okay, so 45 degrees in the first quadrant. Okay, now again, I don't have any ordered pairs. I don't know what that x comma y is. But if that's a 45-degree angle and this is a right triangle, I don't care what that point is. I know no matter what that point is, the x and the y are going to be the same, because in a 40-40 or 45-45-90 triangle, aren't those two legs both end? And what's the hypotenuse? And radical 2. And radical 2. Okay, so if that's in radical 2, so now, let's answer the question, not what cosine of 135 is right now. Let's ask the question, what is cosine of 45? Because the cosine of this angle here is going to tell me everything I need to know about the cosine of the green angle theta. So what is the cosine of 45? Well, if I look at my picture, cosine is adjacent over hypotenuse, right? So that's 1 over root 2. If you want to rationalize that, you can. Okay, so taking your calculator out, if I divide radical 2 over 2, it gives me approximately 0.707. Does that make sense? So the cosine of 135, exactly the same thing, except cosine of 135, because it terminates in the second quadrant, is a negative divided by a positive. So it's not 0.707, it's negative 0.707. Does that kind of make sense, everybody? Now, if you pick your calculator out, and I'm going to have questions here in a moment about, or maybe not in a moment, but at some point throughout the year, well, why can't I just grab my calculator? You just said that it was negative point. Why can't I just take my calculator, instead of doing a lot of stuff that I just did, why can't I just take my calculator and type that in and get my answer? Okay? You're going to see later on there's reasons why I need to know this 45-degree angle and work with it. And one of those reasons is, if this is cosine 135, the question is not going to accept that. The question is going to want negative radical 2 over 2 as your answer. See how they're the same thing? That's the exact value. This is rounded, okay, to whatever decimal place our device will give us. But is that so if I did cosine of 45, is cosine of 45 the same thing as cosine of 135 except for the SIGN? Yeah. Okay. So that's kind of what we're doing here with these types of problems. So every angle that we want to find, so we said this 45-degree angle, that was the supplement of theta. So to find the angle that we're interested in here is that we will take 180 minus theta, if theta is in the second quadrant. Okay, let's do, I know in my notes I've got like a tangent one there. I want to do one more before I get to that one. So let's do sine of 210 degrees. Sine of 210 degrees. So sine of 210, I'm just going to draw my picture again. So that'd be 180, right? How many more degrees do I need to go to get to 210? 30. So I'm going to go about what looks to be a third of that next quadrant. Okay, so that blue angle right there is the theta that we're interested in. Theta is 210 degrees. Okay, but I'll never deal with a number bigger than 90. So I'm going to find a point on my terminating ray. I'm going to draw the altitude. Basically, I always draw to the x-axis. And now it generates that red triangle, correct? What is this angle right there? 30 degrees. You can think of that two ways. You can think about it as the extra amount we went from 180 to get to 210, right? Or you can take your theta minus 180. In this case, it was theta minus 180. If you up here, it was 180 minus theta if I resided in the second quadrant, right? Okay, so in the third quadrant, it's theta minus 1 because theta is going to be bigger than 180. Okay, so that being said, we got 30 degrees here. Can I take that into the first quadrant? If that's 30 degrees, isn't that n, 2n, and n radical 3? So sine of 30 would be n over 2n, be opposite of hypotenuse, right? Okay, so if you knew that ordered pair right there, that ordered pair would be in the format of n radical 3 comma n. Okay, no matter what the numbers were, you could divide the two and you'll find a factor of radical 3 in there. That cancels to 1/2. So that tells me sine of 210 is 1/2. Sine of 30 and the sine of 210 are identical, except for the plus or minus aspect. If I'm in the third quadrant, this y value is actually negative, isn't it? So I go y divided by a positive r, this 1/2 is actually negative 1/2. And that's why when we take our calculator, when we look at sine of 30, I get 0.5, but the sine of 210 is negative 0.5. Does that make sense? Okay. Let's do the one more with the tangent. Tangent 390. So there's actually an added step to this. Okay. 390 is bigger than one complete revolution around the circle, right? Okay. Never deal with anything bigger than 360 degrees. Okay. Our end goal is to get down to something between 0 and 90, right? So if I'm above 360, the first thing I'm going to do is say that the tangent of 390 is identical to the tangent of 390 minus 360. And that will turn into tangent of 30, correct? Okay. So I can think about it this way. If I were to take 390, there'd be 360. That angle there would be 390, right? Okay. Well, if I think about 30 degrees, it'd be that one. Is this highlighted angle right? That's terrible. But is that little highlighted angle there the same as that highlighted angle there? Yeah. So why not work with this one? That's going to be easier, right? So again, if I've got a 30-degree angle here, if that's 30, that's n radical 3, 2n. Tangent of 30 degrees is opposite over adjacent, 1 over root 3. As an exact value, they're going to say radical 3 over 3. Which I think it's like a 0.5 number. So 1.7 divided by 3. So tangent of 30, 0.577. And then you can see 1 divided by the square root of 3. Same number. Tangent of 390. Same number. Okay. So if they were to ask you something of the effect, like let's say we take like 570. Let's say they want the sine of 570 degrees. Well, I'm going to go sine of 570 minus 360. What's that give me? sine of 210. So now it's between 0 and 360, so I'm going to do that thing where I make that angle and say, okay, well, that angle there is 30 degrees, so sine of 210, I'm actually going to work with sine of 30. You see how we started with a really big angle, but dwindled our way down to a 30-degree angle, which is a lot easier to work with? And we should have to pay attention to when we're done. 570 terminates in the third quadrant, because 210 terminated in the third quadrant, so the sine of that is going to be negative. So the sine of 570 is negative 0.5, just like the sine of 210 was. And we could justify that by taking sine 570, and you see we get the negative 0.5 as well. Okay. In this class, a lot of times I like to justify to you guys why we're doing something. I think you can see that and maybe have a little bit more buy-in to it. In a lot of trig classes, you're just taught at first day, well, as soon as you take calculus, remember those signs, those positive and negative values. If you don't really see the relationship and understand why, they tell you, hey, that angle, that acute angle that we always create with the positive x-axis in our terminating array, or the negative x-axis in our terminating array, that's always going to tell us what we need to know about our angle theta, but they don't explain why. Okay? Hopefully understanding the why makes the process easier. No new homework. Have a good day.